Any value would be fine. Make sure that the recording starts and we'll review where we were. Okay, so go back to the PowerPoint. Let's go back up. So the valves of the heart. Okay, great. Why is that doing that? Okay, we'll have here the bicuspid separates the left atrium from the left ventricle. This is called the bicuspid. This is called the tricuspid. This has 3 cusp, and bicuspid has 2. So these chordae tendineae are connected to the valve so that when the ventricles contract, the flaps don't move up and are buffeted or pushed around by the blood coming out of the left ventricle. You want to make sure once the blood has come through the atrium, through these valves, and is pumped to the aorta, the body wants to separate that blood and make sure that the left side of the heart receives blood from the left atrium to the left ventricle. The right atrium sends blood to the lungs through the pulmonary aorta, but chambers have to be separated for proper generation of blood pressure and the whole double pump function of the heart. The heart circulation is very, very important. The heart needs, as I say, the heart has to have oxygen, nutrients, has to get rid of waste through into the venous circulation of the heart. We're not going to ask you about these individual blood vessels, but we will ask about right atrium, right ventricle, and left ventricle. Okay, so let's shut that off. Okay, so we're recording again. So let's keep going. Oop, wrong one. So the heart muscle has action potentials. The big difference is that in nerves, the duration is in very low milliseconds. Heart muscle has the duration of the action potential in order to make sure the heart beats and then relaxes. So the various stages, the first is entry of sodium, and those are voltage gated channels, and they close once rapid depolarization occurs. Then you have the plateau, which makes sure that the long action potential of the heart, because you're in the refractory period, the heart cannot contract again. It has to pump, relax until the next whole process of oxygenated blood coming back to the heart and deoxygenated blood have to be evacuated through the veins. So that's the plateau stage where calcium enters, and the last stage where loss of calcium causes the pH to return to around minus 90 millivolts. So remember, depolarization means when a positive charge comes into the cell, that causes a change from minus 90 to plus 30. This plateau is maintained by the positive calcium entering the chambers of the heart, and the last stage is when potassium leaves, and last stage here when the hyperpolarization occurs. Hyperpolarization means the differences gets greater. So once after about 260 milliseconds, the heart muscle is ready to contract again. If you didn't have this plateau here, and a relatively long refractory period, the heart wouldn't be able to function. It would go into fibrillation, where it's just jittering, the muscles would just be jittering, and the muscles would not allow the heart to pump and then relax. So we went through these three hot processes. So we'll just keep moving on. So notice that skeletal muscle has a very, very short action potential, and that stimulates skeletal muscle. The action potential in heart muscle is much, much longer, and that's so you can have pumping, relaxation, and that relaxation allows blood to enter the body and be up there being, you have that, you have the blood entering the heart into the atria, and then the blood being pumped out of the ventricles to the lungs and to the rest of the body. Understand that action potentials are electrical signals in heart muscles. Those potentials have a much longer duration, and the extended length of this contraction, okay, means that the heart can pump, relax, and then pump again. So how does the heart coordinate pumping from top to bottom? There's a special electrical conduction system that starts the heart depolarization at the sinoatrial node, the SA node, and so these special little nerves start depolarizing very quickly as the top of the heart's going to beat first. So this electrical conduction system's going to carry the electrical stimulus from the top of the SA node. The SA node is auto-arrhythmic. It automatically starts to beat up at the top of the heart. Then the signal spreads down to the conduction system, to the atrioventricular node, and then down to the AV bundle, the bundle branches, and then into the ventricles. So the heart has to beat from top to bottom, and this SA node is automatically depolarizing. In other words, it automatically begins to receive information from the top and the middle, and then the bundle branches going through the AV septum, and blood vessels move to the top of the ventricles and then move down. That way you have contraction of the atria first, then contraction of the ventricles. So all of that controlled contraction from the top of the heart to the bottom of the heart is very important for having an article, meaning to start from the top and go to the bottom so that the heart contracts top to bottom, because the atria have to fill first. So if you trace this SA electrical impulse, you can see it starts in the SA node, and it's ultimately going to go from the top of the right atrium and spread through the whole atrium, and then you have the continuation of the electrical impulse. And as this impulse moves from top to bottom of the heart, the cardiac muscle is stimulated to make sure the heart contracts from top to bottom, and that it's resting between each beat. Otherwise, you'll have fibrillation, and you may have to get shocked with a ER machine. So not ER it has to be shocked by a defibrillator. But the pattern is to have the conduction system carry the impulse from top to bottom, so that atria contract first, and then they're relaxed and ventricles contract. The electrocardiogram, you can put 12 leads, 12 little buttons at various positions, and you have, this is called the EKG trace of the changes in electrical activity of the heart. So the first little, it's called a P wave, that corresponds to atrial contraction, and then you have the QRS wave, which corresponds to the contraction of the ventricles, and then the QRS complex, as I say, is going to indicate the contraction of the ventricles, and then the T wave shows the relaxation of the ventricles. So you can very quickly go to a medical office and they'll attach these leads to various parts, and that picks up the electrical activity of the heart because depolarization and changes in voltage, that's being carried all over the body. So that's the conduction system, and that's monitored by the PQRS EKG trace. The cardiac cycle, which we've talked about before, we'll talk about it again, starts with the stimulation from the conduction system of the heart. The atria fill first, and then the ventricles, and that is pumped out, and then the whole thing starts again when the atria are empty and the blood vessels are carrying blood throughout the heart, but the heart itself is pumping from top to bottom. So ventricular systole means the contraction of the ventricles. There's arterial systole, that means the contraction of the atria, and then you have relaxation of the ventricles, and then everything's empty, and then, well, there is some blood left in there, we won't talk about that now, and then you're going to have ventricular diastole when the ventricles are relaxed, and then you're going to have the atria filled with blood from the lungs, from the body, or from the lungs, and that cycle is repeated over and over again. If you put your fingers right under your chin, right under your mandible, you can feel your heart beating. Okay, let's stop there and go back here and stop recording a moment.